Okay, so today we're going to start the next unit. This is topic 3, thermal physics. We are officially done with mechanics. I know it's been a long time coming, but we can finally move on to a branch of physics that does not have to do with motion. Okay, so topic 3 is way shorter than topic 2. It's also a lot more conceptual and less computational, although there are going to be calculations that we'll be seeing. So this unit has to do with things like heat and temperature and pressure and how objects behave on the atomic and molecular level. And a lot of the concepts that we're going to be talking about should be somewhat familiar to you. You should have learned about some of these things in your other science classes. So for a lot of you, topic 3, thermal physics, is going to be easier than topic 2, just for that reason. So the first thing we're going to do is we're going to take a look at a simulation, and the link to the simulation is here if you want to pull it up on your own. I'm going to pull up the simulation and go through these questions on your own. I would encourage you to, in your notes, answer some of the questions that you're going to see on the next two slides, and try to do that on your own before we go over it, just to see how your answers compare to my answers. So we're going to look at the simulation here in just a second. And again, I want you to leave a space in your notes to answer these questions. So pause here if you need to write them down. Maybe take a look at the simulation on your own and see if you can answer some of the questions on your own. Okay, so the simulation we're going to be looking at looks like this. Okay, this is a PhET simulation. And we're going to be looking, I believe, at different states of matter to begin with. Okay, so in this simulation we have different atoms and molecules that we can see. Each of these dots is an atom. Right now these are neon atoms. We can also see argon atoms. Oxygen and water, these are made of atoms, but oxygen is actually a diatomic molecule. And just to remind you, a molecule is a combination of atoms held together by electrical forces. And so this is O2, and if you look closely, you can see the individual oxygen atoms, but you can also see that they're kind of grouped together in bits of 2. And that's because, again, oxygen is a diatomic molecule. Here are water molecules, and again, if you look closely, you can see the individual atoms, right? 2 hydrogens and 1 oxygen. But make sure you understand the difference between atoms and molecules. Molecules are groups of atoms. Okay, we are going to look at, I think, neon atoms, just because I think they look nicer. And so the first thing we're going to do, you should be able to answer that first question by now. The first thing we're going to do is see what happens as we decrease the temperature. Now, if you look up here, there's a thermometer. There's a way for me to measure temperature. Okay, and currently we're measuring temperature in Kelvin. That's what that capital K is. Kelvin is the SI unit for temperature, and so that's what we're going to be seeing the most often. I can also change it to Celsius if I want. The Celsius temperature scale we don't use too much in this country for some reason, but a lot of other countries, especially in Europe, use Celsius, or they might call it centigrade. That's the same thing. In the United States, we tend to use Fahrenheit. Now, Fahrenheit is not really good for scientific purposes. Like I said, the SI unit for temperature is a Kelvin, so primarily we're going to be working in Kelvin. We will see some circumstances later where you can be in Celsius or Kelvin, but you can't really be in Fahrenheit for any calculation purposes. We are going to talk about unit conversions later between the 3 temperature scales, but just know for the most part we're going to be working in Kelvin and to a lesser degree in Celsius. So what I'm going to do is I'm going to cool down the substance, and I want you to pay attention to the temperature change. And as the temperature decreases, I want you to pay attention to how the motion of the atoms change. Now, when I say the motion of the atoms, I don't mean this whole blob as a whole. You might notice the whole blob keeps bouncing sometimes. I mean the individual little balls that you see there. Each one of those is an atom in the simulation. Okay, so I want you to notice as I decrease the temperature how the motion of each individual atom changes. Okay, so here we go. I'm going to cool it down. You'll see the temperature drop. Okay, it drops pretty quickly. Notice how the motion of the atoms is changing. I'm now at 1 Kelvin. I'm now at 0 Kelvin. And notice as I try to decrease the temperature more, nothing happens. Okay, so we'll talk about this later, but you cannot have a temperature below 0 Kelvin. This is actually called absolute zero, and the reason it's called absolute zero is it is by definition the lowest possible temperature you could ever have. That's just kind of how it's defined. Notice right here, because this is one of the questions, we're at 0 Kelvin. This is called absolute zero. What do you notice about the motion of the atoms here? Okay, so let's look at our question. What do you notice about the atomic motion at a temperature of 0 Kelvin? This is called absolute zero. Hopefully you notice that the motion of the atoms has stopped. Whereas before, each individual atom was moving, it was kind of vibrating a little bit, it was shaking, it was jiggling. At 0 Kelvin, at absolute zero, the atomic motion ceases. And by the way, in real life, we can't actually get to absolute zero, it's not possible. But theoretically, if we could, 0 Kelvin, absolute zero, would be the temperature at which all atomic motion stops. Okay, so that answers that question. As we increase the temperature by a few Kelvin, what changes about the motion of the atoms? Okay, so I'm going to slowly increase the temperature. Notice, by the way, the whole blob just kind of floated up. Ignore that. We're not concerned about that. We're concerned about the motion of the individual atoms, not the group as a whole. In this unit, we're going to be talking a lot about things like kinetic energy and whatnot. Keep in mind, when we're talking about the kinetic energy in the context of thermal physics, we're not talking about the kinetic energy of the entire object, but rather the kinetic energy of the individual atoms or molecules. Okay, so ignore the fact that the whole blob just kind of flew up off the bottom. That has nothing to do with anything. Instead, look at the motion of the individual atoms. Okay, notice I'm at 4 Kelvin. Look at what the atoms are doing now. Okay, they're vibrating. Okay, they're jiggling in place. As I increase the temperature more, notice what's changing now. Okay, they're vibrating faster. Okay, if I increase the temperature more, they're vibrating faster still. Notice that at some point they go from being kind of nice, neatly packed and packed together closely. Now they're still kind of together, but now they're kind of like flowing past each other, so to speak. And so this is what we would now call a liquid. Okay, in a liquid, the atoms are still kind of held together, but they're not locked in place like they are in a solid. And so now we're at 24 Kelvin, which is actually a very low temperature. That's negative 249 degrees Celsius. This is because neon is typically a gas at room temperature. Notice as I increase the temperature more, the atoms start to shake so fast that they kind of shake each other away from each other, and they start to break apart from the pack. Here, we still have kind of a glob of liquid, but some individual atoms are starting to break apart from the group and kind of bounce around their container. And so what I would say is this is now kind of like a mixture of a gas and a liquid. Okay, this part down here is kind of liquidish. This is a gas up here. Typically, anytime you have a liquid, you have a thin layer of gas kind of floating above the liquid. So that makes sense. As we increase the temperature more, the liquid starts to evaporate, and now we have just neon gas. And again, notice as the temperature increases, the individual atoms tend to be moving faster. Okay, there we go. Now I've got a full neon gas. Okay, so we've talked about what happens as we add heat, what changes with the structure of the atoms. So now let's take a look at the next slide of questions. Based on our observations, what do you think temperature is a measure of? Okay, so before we talk about this, based off of our observations, I want you to say, what do you think temperature is actually measuring? And it's okay to be wrong. I don't want you to look it up or anything. I just want to know what you think based off of what we've seen so far. So pause here for a second to answer the question. What you think temperature is based off of what we've just seen over the last few minutes. Okay, so I will tell you the answer actually. Temperature, and we'll see this definition later, temperature is a measure of the average kinetic energy of the individual atoms or molecules making up an object or making up a substance. Okay, and I'll say that one more time because definitions are important, and we'll see this later in the notes. Temperature is a measure of the average kinetic energy of the atoms or molecules making up an object. Now, again, that's not the kinetic energy of the whole object. If you throw a ball through the air, the ball doesn't increase in temperature, but it's a measure of the average kinetic energy of the atoms or molecules making up the ball. Okay, so that answers the first question. Now, the second question, we're going to switch our simulation to phase changes. And what we're going to look at now is pressure and what happens with the pressure as we do some different things. So notice right now I've changed the situation a little bit. I've got a slightly different container, and I have a pressure gauge up here. And again, we're just making observations. Okay, right now we can observe that number one, this is a solid. Okay, it's a solid block of neon. We can tell because the atoms are kind of neatly arranged. And the pressure gauge is reading 0. And so what I'm going to do now is I'm going to slowly increase the temperature. And I want you to pay attention to that pressure gauge and see if you can pinpoint. Oh wait, the pressure just spiked up to 0.8. And now it's back to 0, and now it's 0.7. Now it's 1, now it's 0.3. Can you figure out what it is that's causing the pressure to spike up? Now it's 0 again. What is happening inside this container to make the pressure go up? Okay, so see if you can answer that question. Okay, so hopefully you realize that the pressure kind of spikes up a little bit every time one of these gas particles hits the container walls. And so what we're going to see is as I heat it up more, it starts to change from a liquid to a gas. You have more collisions with the container walls, and this pressure starts to increase. ATM, by the way, is a unit for pressure that's called an atmosphere. There's other units for pressure that we'll talk about later, like PSI or kilopascals. This is just one possible unit for pressure. So right now I still kind of have a liquid. I still have some gas vapor bouncing off the container walls, but I don't have too much pressure yet. As I increase the temperature more and it really becomes a gas, you'll see the pressure is going to increase quite a bit, right? Because now I have way more gas particles colliding with the container walls. Okay, so notice you really only have pressure here when you're dealing with gas. Okay, now the pressure is going up more and more and more. Okay, it's about 30 atmosphere now, 40 atmosphere. Okay, so let's make some more observations. I have a pump here, and I'm going to pump more neon atoms in. And I want you to pay attention to the pressure and see how the pressure changes as I pump in more atoms. Okay, so what is happening to the pressure as I pump in more neon atoms? Okay, so hopefully you've realized that the pressure is increasing as I pump in more atoms. And the reason for that is we saw before that there is a little spike in pressure every time one of those gas atoms hits the container wall. So if we have more gas in the container, that means more collisions, that means more pressure, right? Now one more thing I want to show you is what do you think is going to happen to the pressure as I decrease the volume of the container? As I take my finger here and I push the top of the container in, what do you think is going to happen to the pressure of the container? Okay, so let's see. I'm increasing the pressure by pushing in the lid. If I pull the lid up, the pressure goes back down. So notice that based off of our observations, I kind of gave this away already, but based off of our observations, hopefully you recognize that the pressure in the gas has to do with the frequency of collisions between the gas particles and the container wall. And that's another definition, by the way. Right? So pressure has to do with measuring the frequency of collisions between the particles making up a gas and its container wall. At least that's one way of understanding what pressure is. We'll talk about other ways of understanding pressure later on. Okay, so there's basically three ways we can change the pressure of a gas. Either we can increase the temperature, right? If we increase the temperature, and temperature is a measure of the average kinetic energy of the particles, if they move faster, they bounce off the container walls more often. If I add more if I add more gas particles, there's more collisions. Oh no. The pressure got so great that I blew up the lid. Let me fix that. And the third way is if I decrease the volume, that means there's less space for the gas particles to move around in. That means they're going to hit the container walls more often, right? Just because there's less volume. And so there's going to be more pressure. And so those are basically the three ways you can affect the pressure of a gas. And later we'll see how you do calculations with that kind of concept. Okay, so those are all based off of the simulation that we just saw. Now, just a few more slides, and mainly I just want you to add these things into your notes. But we've kind of seen these things already. All substances are made up of atoms or combination of atoms, that is molecules. These atoms, as long as they are at a temperature above 0 Kelvin, are always in a state of random motion. Now, in a solid, that random motion might look like shaking or jiggling or vibrating. In a gas, it's flying around, colliding with each other, colliding with the container walls, etc. Here is the definition of temperature. I do want to remind you that definitions are important. The absolute temperature of a substance is a measure of the average kinetic energy of the atoms making up the substance. Please don't forget the word atoms or particles, okay? But I would prefer atoms or molecules. A lot of people always remember the kinetic energy part, but not the atoms part. So please make sure that you include that. Okay, this one concept can be used to explain a wide range of phenomena. So we already saw how phase changes happen as the atoms increase in temperature and they shake faster, right? They start to kind of shake themselves apart, going from a solid to a liquid to a gas where they're completely broken apart. When you pound a hammer on the ground gets warm. And you can understand that because if you think when you pound on the ground, you're transferring the kinetic energy of the hammer into the atoms making up the ground, and into the atoms making up the hammer as well. And so that energy basically makes those atoms shake faster, and if they're shaking faster, if they're vibrating faster, that corresponds to an increase in temperature. Okay, so that's why if you pound a hammer on the ground, both the ground and the hammer get warm over time. How a cup of coffee is cool. So just this is not the completely accurate simulation, but just to kind of understand how a cup of coffee is cooled, here's basically how this works. Okay, so let's say you have a liquid. Okay, this is a gas, but let's just pretend you have a liquid. And notice there is a container on top. Okay, and so all of the atoms are kind of trapped inside. Now, a cup of coffee, of course, in real life would not be covered. So I'm just going to cool this down until it's mostly a liquid. Okay, just to show you how you would cool a cup of coffee or a cup of soup. Actually, let me do this. What I'm going to do is I'm going to blow the top off. Okay, and inside a liquid, remember that most of the atoms are kind of glommed together, like down here. But typically what you see, if you imagine a cup of coffee, is you have the liquid part down here, and then at the top you have a few of the more excitable gas particles that are so energetic they've actually left the liquid and become a gas. Okay, and so typically if you think like a hot bowl of soup or a cup of coffee, you see that at the very top of the liquid, kind of flying off into the air. Now, those particles fly off into the air, and some of them come back. Okay, and so, some of them leave, some of them come back. When they leave, they take their kinetic energy with them. When they come back, they leave their kinetic energy, or they bring their kinetic energy back to the cup of coffee. Now, remember that these gas particles on top of the cup of coffee have a lot of energy. In fact, they have the most energy, which is why they were gas particles to begin with. And so if you were to blow them away so that these gas particles could not come back, that means the kinetic energy they had is gone from the liquid. So what does that mean if the liquid has less overall kinetic energy? Well, that means lower temperatures, right? Because temperature is a measure of the average kinetic energy of the atoms making up a substance. So if you take a cup of soup or a cup of coffee and you blow away right up here, the top layer of those most energetic atoms, so that they can't come back and rejoin the cup of coffee, you're basically removing that kinetic energy from the cup of coffee, and therefore you're going to cool down the cup of coffee, and you'll be able to drink it because it's cool enough to drink. So, just this basic understanding of everything that's on this slide helps you explain a wide range of phenomena. Okay, and I'm just going to leave you on this slide here so you can add these definitions to your notes, and we'll start up here in the next video with these definitions.